Everyone, if you could take your seats, we'll go ahead and get started. We're now on the panel on evaluating measurement technologies, and it's going to be moderated by Thomas Fox. And also, I'll turn it over to you, Thomas, and we have until 25 past the hour.
Great. How's the sound here? Okay, we're good. Thanks so much for everyone to be here and for having me. I'm really excited about this event. Have learned a ton in the last couple of days. Mostly, it's that category of the more you know you don't know. So hopefully we're getting closer to some solutions. But alas, this panel is more about how much we don't know and how much we know about technology and how it works. So I guess just to situate things a little bit, and I would encourage everybody to get onto Slido and start asking questions. I would love the audience to be driving the question period here and to vote for the questions you like best. But just to situate things first, I think we all kind of recognize that we are tackling a really difficult challenge in a moment of immense and rapid change, and there are lots of things, lots of moving pieces that are changing at the same time. So one of those things that's changing is technology. If you look at the innovation landscape over the last 5 to 10 years, things are bonkers right now. I mean, I heard that there's like robot dogs now with lasers on their heads, and I met a company the other day that's building blimps and putting methane sensors on them and shooting lasers at the sun and all kinds of stuff. So the traditional categories of continuous monitoring and satellites and drones, even though that we call them alternatives still, is continuing to expand. And the thing is, we think about those categories, but there's really immense diversity in the form and function and the data, the information products that emerge from those different technologies and work practices, depending on how the technologies are used as well. The other thing that's changing is our goals. And so we're moving kind of from a world in which we are leveraging a lot of these technologies to detect emissions events and then resolve them, to a world in which we're estimating the emission rates associated with those detection events and then trying to infer what a company's annualized emissions are from a number of snapshot measurements or some set of incomplete data. And so these objectives are really important to understand as we work towards understanding how effective technologies can be. And then finally, the other big change is the consequences or the stakes at play here. So we're moving from a world in which companies would add up their inventory data maybe once a year with the help of a consultant and send it off to the EPA, and the exact number didn't really matter that much, to a world in which companies' bonuses are not just executives, but the entire company are tied to emissions reductions performance, a world in which boards of directors are asking for quarterly reports on what emissions are, and they want accurate numbers, and a world in which those numbers are going to be used to potentially determine how much methane fee companies have to pay. And so I think one of the things on a lot of people's minds is all of these presentations and the posters have just been so fantastic at showing us, revealing how much uncertainty there still exists in understanding what these technologies can do. And when you think about the potential of taking where we're at now and then leveraging some of that information, for example, to communicate a company's intensity, or even to calculate a methane fee, there's still a big gap and there's still a lot of problems that need to be solved. So to that end, I'm really excited for this panel. We're going to explore how much we know about technology and what the gaps are that remain in order to continue to solve some of these challenges. I'm joined today by a very distinguished panel. We have Damon Burt, a project manager and co-Canadian, I recently discovered. Even though Damon is living in Oslo and working with Carbon Limits, he's Canadian, and Damon's been working, and he's going to share some really amazing work that they've been doing internationally to document what technologies are out there and help operators and regulators understand the breadth and the diversity of those technologies. Second, we have Dan Cusworth from Carbon Mapper. I've been following Dan's work since the early days of my PhD and have always been a fan of Dan's work, and he just keeps kind of doing cooler and cooler stuff, so not going to ruin any surprises, but some cool presentation work today. And then obviously Dan Zimmerly, who doesn't even need an introduction. He's kind of the godfather of methane in many ways. Before I ever even met Dan, I met Adam Brandt, and the first thing Adam Brandt said to me was like, yeah, Dan Zimmerly, he's like my hero, man. And so really excited to have this panel. I'm going to pass it off to Damon and look forward to all the presentations.
Great, thanks Thomas. So good afternoon everyone. My name is Damon Burt and I'm a consultant with Carbon Limits. So we're a consultancy company based in Oslo, Norway. And so a lot of the work that we do is related to climate change mitigation, and so more specifically decarbonization of the oil and gas sector. So we work with NGOs, governments, development banks, as well as private companies or industry associations. And so a lot of the work we do is related to capacity building and training, techno-economic assessments, as well as inventory development and emissions mitigation. And so part of the work and the important aspects of this work is that being able to have mitigation, you have to be able to measure something in order to be able to reduce it in the first place. And so we get a lot of questions about specifically, the number of technologies that are available and out there for detection and for quantification. And so also questions about how do we deploy these technologies? How can they be used to detect, quantify, and ultimately spur emissions reductions? And so I've had the opportunity, along with Carbon Limits, to develop a recommended practices for methane emissions detection and quantification technologies on behalf of OGCI, IOGP, and IPCA. And so the goal of this is it's targeted for upstream oil and gas operators within a global context. So I'd like to propose a scenario for you. Say that we have Ali, the process engineer. Ali works for a small oil company. I won't say where, but let's say it's not in North America. Ali's been asked to develop an inventory so potentially using measurements. But there's half a dozen other things to do at the same time, so the amount of time available to do that is, there are many different things to do. And so, doing a quick Google search, it can seem overwhelming with the number of technologies that are available, what's out there, what are the capabilities. Can you use OGI cameras, that you already use for LDAR? How do satellites or aircraft or drones factor into this? There's also these continuous monitoring solutions. How do they factor in? And so the goal of this report is that it provides a framework for oil and gas operators to have a better understanding of the information that's out there, to address potentially identifying relevant technologies that they could use to both develop an inventory, but also to reduce emissions. So the report is, it's accompanied by a series of decision trees so this could be for source level, site level quantification, as well as reconciliation. I think Colette gave a good overview of what these are before, so I will defer to her. So similarly, the report also identifies, potential avenues for technology deployment and what should be considered. So it's accompanied by a technology data or technology filtering tool that plays host to, I think currently we have approximately 50 technologies included in this that based on, site specifics or operator preferences to be able to help narrow down and identify potentially relevant technologies that could be useful for deployment, for emissions reductions, for inventory development as well. So it's accompanied by references and links to the information, all which is publicly available. And so the work that we did, so through Carbon Limits, but also with interviews with technology providers, with service providers, with operators, as well as basing on peer-reviewed literature and researchers as well, to try and give a a well-rounded sort of view of technology capabilities at the time that we worked on it. All with the ultimate goal of identifying, how to effectively reduce emissions within a global context. And so the report is publicly available. It's available and was recently released approximately 2 weeks ago. So I would encourage all of you, if you're interested, to go look for it and download it. The technology filtering tool is also available, and also open for any questions or considerations for that, also for future improvements as well. But that's all I have, so I will throw it back to Thomas.
Thank you so much, Damon. We're going to go to Dan C. next. I believe there's slides. You have slides, right? I don't know where the clicker is. Do you want him to get up and?
Maybe it's over here. There are slides. Yeah. So while it's getting ready, I'm going to do something that's probably very ill-advised and is, it might make you all not like me, but I do want to say California is a wonderful place to live. So if any of you are thinking of that, just keep that in mind. Surf in an ocean or something, Anyway, okay. I got the clicker. It's coming up in 1 second. Okay. So thank you so much for having me. This has been just absolutely phenomenal. A couple of days to learn about a lot of things, and to see so much really critical work. I want to just talk real briefly, not too long, about Carbon Mapper. What we are as a system, and the surveys that we've done, the data that we've provided, and what we plan to provide. And so when you hear Carbon Mapper, I'll try to go quickly with this, kind of refers to two things. One, there's Carbon Mapper, the NGO, which I'm part of. So this is a nonprofit, non-governmental organization with the goal of providing data publicly of carbon dioxide and methane, in particular point sources, freely available for people to see. There's also a coalition, Carbon Mapper, a coalition, and this is a public-private partnership amongst various different interested and invested parties, primarily being us, Carbon Mapper, the NGO, also Planet Labs, NASA JPL, in addition to RMI, CARB, and several philanthropies. So this coalition is working together to launch several satellites, the first of which should go up in 2024, again, to get global coverage, primarily of methane and CO2 point sources, and to make the data freely available. And is public-private, so there's a private component of this, which is a rapid leak detection service that is offered through our private partner Planet, but all methane and CO2 products that we observe with our satellites will go publicly on our data portal. Since the topic is about measurements and validation, I just want to show a few activities that we've done. We've talked about blinded controlled release experiments. These are absolutely critical. Just as critical also is what Matt Johnson was talking to with regards to probability of detections. So when you say you can have a minimum detection limit for an emission rate, that's great, but what are you routinely observing, and how do we quantify that, and what does that mean as we're trying to scale up at a facility or across a basin. And so these are just some examples of controlled release experiments that we've participated in. It's not the only thing out there. You got to, coincident measurements with other aircraft or other systems in order to corroborate or show divergence are also supremely critical to this type of endeavor. So on a plot on the left, I know we're talking oil and gas, but landfills are near and dear to Carbon Mapper's heart as well. And so these are a series of dozens of landfill simultaneous overpasses that we flew with scientific aviation across the United States to compare and to see. Scientific aviation is more a mass balance approach. They would quantify more total emission of a facility or a set of facilities. Carbon Mapper here using the GAO, Global Airborne Observatory, we're more of a point source imager. So we don't necessarily expect these to be exactly the same, but they should be in the same ballpark, especially if we're dealing with a large set of landfills that are showing point source emissions. On the right, I'm showing you some raw fairly preliminary data of us coordinating our aircraft campaigns with the NASA EMIT instrument in the Permian Basin. So really knowing exactly when the satellite, which was very difficult because that's on the International Space Station, which has a very strange orbit, but timing it exactly so that we could go over a site that we had observed for about 4 years and knew was a persistent emitter, and got, I guess, lucky on that day that it was also a persistent emission source, a compressor station, so that we could do instrument intercomparison to make sure that we're on the same track. Here's some high-level statistics. It was really interesting talking with, hearing the talks and talking about the goals of MDEL is how do you bring multi-scale or multi-tiered observing together to try to derive some insights. So we've done some preliminary tests with this well, I shouldn't say preliminary, some pretty extensive airborne campaigns across the United States in 5+ basins where, if you're counting site measurements, this is about 1 million site measurements across basins. When we are flying our airborne campaigns for this type of survey, we're flying them a little bit higher so that we can do comprehensive surveys. So this is very important because when we're talking about, well, every basin's different and what's the minimum detection limit of a certain basin, you have to make sure that if there are the opportunities for 1 in 1,000 events within that basin, that your sampling strategy is broad enough that you are capturing with enough statistics those 1 in 1,000 events, or else you might bias low what you think's happening in that basin. So for these surveys, we were trading sensitivity for spatial because we wanted to capture those events and know that those were there. And what we found is that actually in every basin that we flew, there was a significant fraction of emitters above 30 kilograms an hour, so much so that when we compared them to a regional budget using a satellite information, a total flux using the Tropomi satellite, which are these blue bars, and compared it to our point source component, that we were finding that about 20 to 60% of all of the emissions were driven by these emitters that were above 30 kilograms an hour across all basins. And that's what the red bar is. And then on the last bar in each of these is what the bottom-up gridded inventory would tell you. And as you can see, recurring theme, there's quite a divergence. Now you can argue a little bit on those red bars of did we get the intermittency right? But again, we were flying tens of thousands of pieces of infrastructure across this basin. And one thing that we did find, because we surveyed over the course of weeks to months, to in some places years, is that there were some persistent sources that were large that made up about half of that budget. So if you're saying 40% on average came from the point sources, we were seeing about 20% coming from persistent sources. There's more that we do with imaging spectrometers. I could go into a huge amount of detail. I don't have the time, but one thing that's near and dear to a lot of our interest is combustion efficiency. A benefit of imaging spectroscopy is that you can retrieve large CO2 signals as well, and you can retrieve flare signatures as well. So the example on the top is a cogeneration plant. Same overpass, saw methane and a CO2 plume. You can compare those to get a sense of what the efficiency is at that facility. On the bottom is we were flying in the Bakken, and we had Stanford University was on the ground with a bunch of FLIR cameras looking at flares at the same time that we were flying. The plot here on the left are methane plumes that we saw. The middle plot is them looking at the flare. You can see that big ball of fire, and then the resolution's not great, but you see a little emission coming off as well, and that was something that was corroborated. We can retrieve flare temperatures using imaging spectroscopy. I think that's probably all my time. I did want to just do one last thing, is the trade spaces for observing systems. So, and again, we've talked about trade spaces. This has been a recurring theme. What's your temporal revisit? What's your detection threshold? And I would just suggest there's a third axis here, which is what's your spatial coverage over all known emitters as well? Are you actually characterizing a basin properly? Okay, I'll leave it. Well, I can go longer. Whatever. Okay, I got one more slide. Okay, so again, like I said, all data products we're releasing publicly on our data portal. So this is just a snapshot of what we have here to go to data.carbonmapper.org. Currently, we have airborne data as well as processing with the NASA EMIT instrument. We plan to continue to update this. So NASA EMIT satellite is a great satellite that's up on the International Space Station. Still trying to figure out exactly what that sensitivity is. We'd say it's ballpark somewhere between 300 to 1,000 kilograms an hour. Of course, it depends on the region, it depends on the wind speeds and all of that. The satellites that we're launching, they are legacy from EMIT, but they have much finer spatial, well, much finer. There's a 2x improvement in spatial and a 2x improvement in spectral resolution, which we think will result in about a 4x improvement in detection limit. But of course, these things have to be tested. But all of these products will go on our data portal. And again, the point is that right now, with 2 satellites, we can probably do a month or 2 months of sampling at every major target globally that we think that where there's potentially oil and gas point sources. We want to build this constellation out so that we can get this down to weekly and in priority regions that are really important, potentially daily. Okay.
So I'm going to go through a few results from our work characterizing leak detection and quantification. And so as most of you may know, we run the Methane Emissions Technology Evaluation Center at CSU, and as part of that, we test a lot of leak detection solutions, probably north of 60 or 70 of them at this point. And so what I'm going to talk about today is just sort of tease some results, teasing right now, results for some stuff that should be in publication here very shortly or in preprint. So the whole idea behind a project that we were doing with, funded largely by the Department of Energy was something called Advancing Development of Emissions Detection. And the idea there was we were going to test at METEC in controlled environment or sometimes in other locations under controlled testing and then do the same thing in the field, and we were going to compare those two together. Okay, so this is one of these high-risk projects because you never know kind of what's going to pop out the other side. And so when we went out and started doing the field trials, and we tried to do the testing the same way that and get the same results as that we were doing at METEC, it didn't work. And so we decided to do more of the work with what we call a challenge test, which is that we take the emission, we just take the site as it is, kind of characterize that, then we add in some challenges, which are additional releases. We've done that on all kinds of sites at this point. And then we're going to compare those together with some detailed on-site measurements and stuff. So the whole idea was when we got out in the field, we had a slightly different response than we got at METEC. So what you're seeing here on the plots on the right, the lines that are in blue are the 2023 controlled release testing at METEC using the same techniques that we did in 2022, which is in red. Okay, and then what you see is a couple of solutions that tested in both cases. So the ones on the bottom are sort of the same. So they went 2022 and tested, they went 2023 and tested, and they have pretty much the same detection profile. And then on the top, you see one of them got worse. Actually, their detection probability went down. And the other one actually got better, okay? So what you see is there is some movement as people test multiple times. You can see some change in their performance. The thing that is not captured in this plot, and I just don't have a good way to demonstrate this, is in the process of either being the same or getting a little better or a little worse, people's false positives went way down, right? So people are really working on that sort of detection stuff. So we can kind of pat ourselves on the back now that we had characterized the solution, we knew how they performed. So in the idea here, now we're going to go out in the field and we're going to challenge test it, right? So now this is a dual test, right? Because it's how well did the solutions work? And then we're sort of like running the risk of saying that we didn't do the right thing, okay? So when we go out in the field, we didn't see at all what we saw at BTEC. Zip, okay? Now, so that's sort of a, didn't work the way we expected sort of thing, right? Okay, so that says that METEC's got to up its game, right? Because we're not reflecting the kind of challenge that people are seeing in the field. In a couple of cases, we literally saw no response from the solutions. And we have some theories around why that is. It'll be in a paper that's coming up shortly. And in some cases, we saw a response, but it was much worse than what we saw at METEC. So the first thing is, we kind of have a dual learning here. One is, we didn't do what we thought we were doing at METEC, so now we need to get better at METEC. And then the other thing is that the solutions don't do as well in the field, in field conditions, as they do out in the they do out at METEC. Okay, so we need to close that up. METEC provides a lot of information. It helps us out a lot with characterizing solutions, but we've got a gap that we need to fill. The second study we were able to do was at some midstream facilities where we ran 2 solutions. There's the old thing with man with 1 watch knows what time it is. Man with 2 watches is never really sure. So let's get 2 solutions and go measure some midstream facilities, okay? So when we did this the first time, what you see on the left is we did a lot of stuff with those solutions. So we sent them out and had them do a lot of other work, and they also measured the facilities. Okay, and they disagree with each other on average by about 30%. Okay, so the criticism is, well, you didn't give them enough chance. It's too few samples. Okay, so let's let them work harder. So on the second Bland-Altman chart on the right, okay, what we've done now is basically dispatch the same solutions and have them measure the same facility many times. Sometimes we got tens of measurements. And now that they're working harder and they get more chance, they disagree more. Okay? Now, so that's a little the opposite direction you want to go. Okay, so it means that the solutions are very confident about their answer. They're both very confident about their answer, and they disagree. It's kind of like listening to my grandmother and my uncle argue. They both knew everything, and they never agreed. Okay? So what we got here is a problem, because if you're going to rely on that for measurement-informed inventory, that has an issue. Now that I've picked on everybody, let me give you an idea of why this is so tough. So these images are from a compressor station, overflowing by your favorite top-down solution. Okay, it gets pretty high resolution. And this is every 5 minutes over the same building, and there is really not much happening during this whole period. There's no engine starting, stopping, or anything else. Okay, and it gives you an idea of how wildly different the emissions look just looking at one facility sampled every few minutes. Now, if you could imagine that you're a point sensor, right across the top edge of each image, that's aligned with the fence line. Okay, so where are you going to put your sensor? What are you going to see? And and how will that change every 5 minutes? Okay. So a couple of food for thought items. Our controlled testing was simplified because we weren't quite engaged with the companies the way we wanted to be. And so we simplified things down at METEC quite a bit. And it turns out that we probably need to up the game now, that we have a little bit more. The second thing is that quantification accuracy in general is sort of challenging. I didn't show any plots on that, but you can see it in the paper. Quantification is still a real challenge for people, and you can see from those pictures why it would be that point. And then the last thing is, when we test solutions, we're testing this combination of sensors and deployment and algorithms all integrated together. But the reality is, it's the algorithms that are the problem. So if you think about the challenge of digesting that and producing a consistent number, that is a hard problem, right? And that's really what's challenging people right now. Thank you. Let's see, I think we can get rid of that. I think it just goes away. Okay, good.
I have the first question on my phone, so I'm going to pull it up. But everybody else, upload your questions to Slido. Dr. Allen is monitoring the most popular ones, and we'll be asking him in a second here. So I have a question just for anyone who wishes to respond to this. I suspect there will be some opinions on it. It sounds like we live in a world right now of multiple truths. We often will work with clients on our end and look at data sets from different types of technologies, and we'll see that even when, in theory, their performance should overlap, just what you've said, Dan, and it's actually really timely to see those results for the first time, because it it corroborates some of what we're seeing, is you don't get overlap at all in what the estimates are from
Yeah, but just to be clear, that's not at every site.
Right.
Right. So what you'll get is at some sites there's actually reasonable agreement, if you kind of look at the plots, and at some sites there's bizarrely wide disagreements, right? So something about that facility, some uncharacterized something, has misled one of the methods. So it's kind of a quality indicator sort of problem, where you just don't know when you went off the rails.
Yeah, so no, that's very interesting because what we're seeing is similar, but we're seeing systematic differences across large numbers of sites in terms of what technologies are reporting. So I guess my question is, if I'm an operator and I'm testing out different technologies, I'm looking at the regulations that are coming, I'm trying to figure out what technologies to use. Are you at all worried that there's going to be kind of I don't want to call it like a race to the bottom, but like an incentive to use technologies that give you a more favorable answer? Or do you think we're going to converge into a world where we do have one truth? And what is it going to take to get there?
So I think as we do more studies, and it's obvious who's participating, there is a chance that people will pick vendors that produce lower answers. Okay, so I think that's a real risk. Now, I think on the other hand, most of the vendors most of the solution developers are cognizant of that problem. So I think they will work on their algorithms as well. So it's not like people are standing stationary. But it does call out the need for us to start getting some type of a structured approach where, there is a assessment. I also think that a key thing that needs to be digested by the whole community, and it probably impacts regulators and some of the NGOs who are looking at the results even more than it does kind of the companies, is that these guys the uncertainty here is never going to collapse down to 10%. It's just not going to happen. So what we need to get is used to the idea that individual estimates are going to have quite a range on them, okay? But what we haven't seen yet is kind of the pressure to get the answer in the mean to be right. Okay, so a lot of times when we're looking at quantification, there's a lot of spread, but the spread isn't correct in the mean either. So the average is not converging to the right number. And I think that's kind of a tough problem, because it's easy to estimate high, but down, there's a limit. You can only go as low as 0. And so as a result, if you tend to be kind of off by a factor of 3, your mean isn't 1, your mean is going to be skewed. So what I would say is, what we should do is quit focusing. We don't need to quit focusing, but the focus should be on being accurate in the mean. Okay, because the uncertainty is not going to collapse.
Yeah, can I add to that? So definite great points. I'd add a few things. One, it's a little bit of a pet peeve of mine, right? Is when we talk about technologies, everyone is kind of using what can your technology do, and they're thinking that that's like sensors or photons that hit a sensor, but really it's a technology, a detection protocol, and a quantification algorithm that goes along with that. And there's, where this gets complicated, especially when we're in a public, private space, is what is the, transparency for each of those elements in terms of the quantification. What are the standards that are going to be, into that? What are the error budgets as they're getting reported, and is it a comprehensive error budget, and does that make sense? And I think there is there's a need not for prescriptive standards, but just when you say there's an emission rate, have you thought about X, Y, and Z? Given that when you look at plumes, like Dan was showing up, there's certainly cases where that's going to be quite complicated. I would also say this is where it gets difficult as well. Everyone, we're chasing the minimum detection limit, and what can your sensor do? But if your controlled release was showing, your quantification accuracy was really good, but on everything that was 100 kilograms and above, because those are all these whopper plumes that are, in the well-mixed part of the boundary layer, but all of your uncertainty sits at the 5 kilogram an hour, but you're using the population of statistics to say something about the minimum detection limit, I think that's, where things get a little bit complicated as well. So disentangling these and making it extremely transparent, I think is, critical.
Yeah, and so I'm not going to disagree with anything that's been said previously, but so I think one thing that I wanted to say as well was, so Dan, with the work that you showed, sort of going beyond the controlled release testing at METech to a sort of a field trial and the field challenge, the capabilities of the technologies when they are in representative conditions as well. When you compare the simple, a relatively simple site, and you want to apply that to another setup with other complicating factors, I think there could be 10 different things that might have to come into consideration. And so that's the importance of sort of the representative conditions. It doesn't even begin to start to factor in, is it onshore versus offshore operations, completely different. So being able to trust a technology that, tested at METech, how is it going to perform, elsewhere in North America, outside of North America too. So, just want to say, very insightful.
Great. I've got the Slido here, but you've probably prepared one. So if you want to ask the first one, Dave, go for it.
Sure. So I'm going to combine a couple of questions. Dan Z, you noted that that the control testing needs to get more complex. You also noted that assumptions that get made in converting an observation into an emission rate are very important. So can you comment on two things, and also the other panelists to weigh in on this as well? One is, how would you make controlled testing more complex, either in the METech context or in other contexts, to make it more realistic of what the applications will be? And then second, if you were to put out more data collection that could be used to augment the signals that the technologies have, for example, better wind field characterization, what would you put out?
Yeah, so let's describe why we do control testing in the first place. Okay, so what its role is. So when we bring somebody to METech and they're installed there for 12 weeks, we can get 400 or 500 experiments done. And each one of those is a couple of hours long. Okay, trying to do that in the field, like in a field challenge testing, is virtually impossible. We're lucky to get maybe 30 experiments after being there and harassing the poor site operator for 2 solid weeks. Okay, it just doesn't work super well. So that's one aspect. So the reason we're doing control testing is you get the volume in. Okay, and then the question with control testing then is, how do you make the site more complicated so that it looks like, more like what you have in the field? But at the same time, if we had taken 2017 or 2019 even vintage solutions, dropped them into METech, did everything that you see at a facility, it just crashed and burned. Okay, so that's not real useful for people to develop either. So it's a runway, you got to ramp into it. The second thing that we've spotted is that in addition to just the emissions field complexity in controlled testing, the size of the site and kind of the density of the sensors and that type of thing is very critical. And to your wind field question, and you and I have talked about this so we know where this is going, part of the problem that we're seeing, I think, in general with the solutions is they talk all the time when they probably should be quiet most of the time. Because when they're on a larger facility, that downwind cone angle that the emissions are actually transported to the center is pretty darn small. And so a lot of the time on a large site with 4 or 5 sensors on it, the signal is going between the sensors. It is not hitting the sensors. Okay, and so you have a pressure on the industry right now, and pressure on the solution developers to provide an answer every so often. on some kind of pace, and they really don't have the data to do that. So I think part of what we can do as a industry is to kind of open up the space for people to be more honest about what continuous means. Continuous doesn't mean all the time. It means trying all the time, okay? And then reporting when you actually have the information that you can do something with. And it's the same thing for the aircraft or the satellites. You're gonna fly over and it's gonna be a dud. Okay, we just need to get we need more recognition that that's okay. Okay, but let's just take the quality answers out of it. Then the last point I'll lead with you is that we've learned is METEC's too physically small because people put too many sensors on. When they come to METEC with 12 sensors an acre, and they go out in the field with 3 or 2 or 1 sensor per acre. And so they don't get the same effect. There's more space between the sensors. So part of it's just a protocol change to say you've got to deploy at the same density that you do out in the field.
Yeah, I'll add just a little bit. At least from the remote sensing perspective, and it's similar, is the major driver of error or uncertainty is the wind speed, right? Pretty much every remote sensing apparatus is going to need some sort of wind product that if you're globally minded and you're flying everywhere, you're kind of at the whim of a reanalysis or forecast product, which is at whatever resolution it is. But even if you were to have wind sensors kind of everywhere at the surface, it's fluid dynamics, right? So how would you even parameterize that in a way that's systematic, that makes a lot of sense, and do it in a way that's somewhat operational? So if we're wanting to get something to an operator quickly or to someone very quickly, that you've made sure that it's good enough. And I think this goes back to the first point, which is just, what are the uncertainty requirements on the use case that's at hand to do some sort of action? And then what is the latency demand on a data product given that use case? And thinking of uncertainty and what can we do with what we have versus what needs to be improved based on that. Also to Dan's point, in places that you're just like, gosh, at least from our perspective, that plume looks like junk, but if we think it's methane, maybe feel comfortable with just saying, I'm just not even going to do an emission rate, right? We're just let's call it a detection and move on, and we'll get it in the next pass, right? And being just kind of open about this is what the technology is giving you.
So yeah, I don't know how to add to that. When we have the Godfather and.
Answers you can't refuse.
But so yeah, all I want to say maybe is so this the recommended practice report that I talked about previously. So a lot of the information, so it's based on some of the amazing work that's coming out of North America as well, and so the people I'm sitting beside up here as well. And so, but it is a fast-moving space. The report that we published was finalized sometime last year. In 8 months, the amount of what's occurred sort of in that time as well. There is leaps and bounds, I would say, compared to previously. So there is just a lot going on. It's quite exciting.
Dave, we're 1:20. We're wrapping up, or I can't remember the time.
So I have in the back of the room, I'm seeing 1:25 that we're wrapping up.
Okay.
So we
So you got
have
a few
about
minutes.
a little less than 15 minutes.
Great. I'm going to skip the most popular question because I find it triggering, Alex. It's about how hungry I am right now because we haven't had lunch yet. But I'm going to go down the list. The second most popular question that's been upvoted is targeted at Dan, which is a little confusing because we have 2 of them. But we'll open it up. Will grandmother and uncle ever agree? And I think we've kind of touched on this theme a little bit here in terms of kind of what happens for specific technologies in specific instances. But in a regulatory context, what do we do if we never get to the point where we have agreement among solutions and technologies? It feels like we're at a point right now where we are forging ahead anyways, Are we getting ahead of our skis a little bit, do you think, in terms of, from a regulatory context, in terms of what we can actually accomplish with these various solutions that currently exist? And yeah, maybe I'll just stop there.
Yeah. Well, I think at $900 a ton, pressure on it getting the right answer and not just an answer is going to go up. Okay, so I think that's the reality, that we're going to have to. There's going to have to be pressure on people to converge. Now, I had an aerial company tell me just a couple weeks ago that they didn't want to be involved in any more paired measurements because they were tired of shootouts. Okay, well, I think that attitude is not going to fly, right? Because when we're doing paired measurements is actually when we're starting to find that there are some issues. So I think part of it's going to have to be institutional pressure to bring people to the table. I hate to say that, but at some point, folks are going to have their feet held to the fire, and there's got to be an absolute standard, right? I mean, it's not a very popular thing to say, but millions are on the table now. So,
Potentially billions,
yeah.
Quick question for you, maybe, Damon. Now that you've coming to visit us and seeing all this complex stuff that's happening, which I'm sure you're aware of in your research, what's the next step for the database? What's the next step for the report? How can we start to kind of enhance this resource for operators?
Yeah, absolutely. So the report, so as I mentioned, was finalized sometime late last year. Like I said, 8 months, 9 months have gone by. The changes that have gone on. So the goal with the report is that it will be something that we keep. I call it evergreen. So with continual updates, so that it is relevant with. So some of the research and some of the work that's going on, that it reflects that over time as well. And so anyone who has any input or feedback, I'd be more than happy to talk to you about that and be able to keep it up, keep the information as up to date as possible, because it's a resource for stakeholders. Input is more than welcome, and so I'd be happy to talk about it with anyone.
Great, thank you. So when it comes to testing, and especially, so there's a question here about more complex evaluation. I think this is something that a lot of groups are starting to think about. One piece of feedback that I've heard from vendors about controlled release testing, which I'd be curious to hear feedback on, is whether certain types of testing protocols may inadvertently favor one type of technology over another. So I guess dual question here, but as testing becomes more complex, how do we mitigate the risk of favoritism, I guess, in experimental design?
Yeah, thanks. You gave me an opening for an advertisement. Okay, so as part of the added program, we're working off of protocols. I think probably most people are familiar with the fact that those are on our website, and we've been using those. They actually came out of a meeting that you and I ran like 1 million years ago. And so what we're going to do is we need to open those protocols back up, because what Thomas said is exactly right. So the metrics that are being used by solutions to kind of capture their value in the field is not necessarily what we thought the metrics should be in 2019 or 2020 when we put those protocols together for the first time. So starting in December, we're actually having a series of meetings. We're going to try to bring the whole community together and do a rev to the, probably not so much to how the testing is done, though I'm sure there'll be some tweaks, but more to kind of how the evaluation metrics work. The other point is, I think we want to be a little careful too about the fit for purpose. What we talk about, we mix together here probability of detection and quantification accuracy. And solutions can be very useful and really crappy at quantification, or not even do it, right? Because they're good at detection. And so part of what we also need to understand is when we evaluate when those metrics come out, there may be quite a few distinct niches for deploying stuff, right? So it doesn't necessarily have to be that you're good at detection, you're good at quantification, you can be on a bunch of different site sizes, and you can do pipelines. No, okay, there's some subset of that.
So maybe I'll target this one to you, other Dan, and others feel free to weigh in. So there's a lot of questions and emerging conversations around algorithms, and you kind of alluded to this point where a lot of people might see, oh, technology X produces answer Y, but there's a whole lot more that goes into getting answer Y that is often not appreciated. So there's a question here around kind of the importance of atmospheric stability and dispersion modeling, but more broadly, and just tying in another question now, what would you, if you had to choose what was more important, would you say it's the evaluating the kind of the integrity of the algorithms themselves and when they work and when they don't work, or would you say that focusing more on detection sensitivity is more important?
Oh yeah, well, I'm not going to say one is more important than the other. I mean, obviously these are both very important, but I will, I'll coming from an atmospheric science background, there's a lot of years of experience with many other data systems and derived products. We'll call these, sometimes these are called like L4 products, and in space system parlance, but these are derived products that are coming from concentrations, et cetera. And, in particular, I'm thinking of, fluxes, global fluxes you might get from a CO2 sensor. That there are massive model intercomparison projects that exist where people kind of put out on the table everything that they did to get to a solution, and then there's an investigation where the differences are. That doesn't really exist for the point source imager plume detection yet. And it's very complicated with it being kind of in a public-private sphere and who's doing it. But I almost see that there's an extension of any controlled release experiment that might happen with multiple technologies, that there should be a reconciliation component of that as well, where you kind of say, hey, let's lay out on the table what this looks like and probe what the uncertainties are and how we're dealing with them. The hope is that kind of a rising tide would lift all ships here, because there could be things that, hey, I thought my sensor could only do this, but look at this, actually can improve my quantification accuracy if I'm considering transport in a different way, or dispersion, et cetera. And I think that's kind of required if we have to get the grandmother and the uncle to talk to each other. It just has to be done in a way that works for a variety of users that obviously have very different motivating factors. On the detection front, also that is algorithmic, right? I mean, at the end of the day, most of these are observing photons, right? And so there's some noise that's happening, there's some retrieval algorithm that gets to a concentration. Every technology is going to be prone to its systematic errors, et cetera. If there's smart ways to take that into account, that actually could potentially push down detection limits across the board. So it's very important as well. But.
Okay, I'm going to ask one more question, and I think this is kind of inspired by a paper, Dan Zimmerli, that you wrote a while back, where you evaluated OGI effectiveness for trained and untrained, and very curious about the human dimension of technology performance. This is something that we don't often test for, and is very difficult to test for. Obviously, there's variability among different technologies, but I guess open question, and feel free to wrap in any closing thoughts as we only have a few minutes left here. But what is the importance of human dimension in control testing and evaluating technologies? And maybe for you, Damon, is this something that that you think should be considered, or that you did consider it as part of your analysis in your report? But maybe we'll start with you, Dan, and then work down.
Yeah. So on these 5-minute overviews, you can't get into all the details, but one of the things we see is that when we test at METEC, we require the solution developer to send us detection reports. So they have to interpret their dashboard or whatever they have, and they send us the interpretation because we don't want to be biased in interpreting their dashboards. When they sell that same solution to a company, usually the dashboard that they have doesn't produce those detection reports and that quantification report. It reports some sort of time series of somethings, and then it's left as an exercise to the company how to interpret that. And that is like 100% human factors. Okay, it involves, it's a trying piece of data to look at. It's hard to interpret. The people who are doing the interpretation are not necessarily the ones who, that's even their main job, right? And so now you get a completely different variable on performance. And in the plots I showed you, that had already been removed. Okay, so those plots were with us actually going back to the original dashboard and interpreting, putting some thresholds on and some very precise numbers to get that red line that didn't match up with the blue line. Okay, so the reality is it's even more challenging in the field than what we're capturing.
And so, yeah, I would say, so the OGI paper that you did refer to, so of course, yeah, so that was something that we drew upon for the report as well. Human behavior, very important as well. Yeah, all I would say is that it's, yeah, as more and more information becomes available, that's, anything useful that could be shared sort of with a wider audience, with various stakeholders as well. Yeah, whether that's the technology or if it's, the operator or the user, it all factors into play, and so it's something that we're going to be looking at as well.
Dr. Allen has risen, so please join me in thanking your hungry panelists.